This is the, yeah, hi. My name is Shiva Kasiviswanathan, and the title of the talk is Restricted Eigenvalue from Stable Rank with Application to Sparse Linear Regression. This is joint work with Mark Rudelson. So we are going to work in a high-dimensional setting where the dimension of the data is much greater than the number of observations. Such setting appears in a lot of applications, in biology, in medical imaging, natural language processing. And we're going to start with a simple linear model in these settings. So we're thinking of Y as being an observation vector. M is a design or a covariate matrix with n observation. Each observation is d-dimensional, where d is much greater than n. Theta star is the unknown vector underlying the linear model, and this W is an unknown noise vector. So that's the setup. So Y is m theta star plus W, and the system is underdetermined, so you can't estimate theta star unless you have some additional assumptions. So a typical assumption in these kind of problems is the assumption of sparsity. The assumption is that theta star is k sparse. So in that, the support of theta star is only on k points out of the d points. So now the goal is, under this assumption on sparsity of theta star, can you construct a theta hat that's a good approximation of theta star? Okay, so this is a well-studied problem. It's very well known that doing this exactly is NP hard. So the typical approach to this is to look at L1 relaxation. And the standard technique to do this is using a technique known as Lasso. This is exactly the formulation. And the question that comes next is that, what can you say about the theoretical properties of this Lasso estimator? So the past decade, we have well-developed theory in this community. So the general picture that appears is that the design of the covariate matrix needs to behave sufficiently nicely for the Lasso estimator to succeed in estimating theta star. So if M behaves sufficiently nicely, we can estimate theta star. Okay, so let me start with a simple observation. So it's very easy to see that for appropriately chosen lambda, which is the regularization parameter, the Lasso estimator, and if you look at the error of this Lasso estimator, that belongs to a set, CS, where S is the support of theta star, and CS is a set of vectors such that the mass on the S complement is not much more than the mass on the S. Okay, and this CS set is a set of if you plot it out, it's a set of the vectors in the CS will form a cone, so this is called as a cone constraint, and this error vector that we are trying to estimate, trying to bound, belongs in this set. Okay, and if you use that kind of observation, the definition of the restricted eigenvalue comes out naturally. So restricted eigenvalue is the weakest condition, or the weakest and the most general condition needed for Lasso estimator to succeed. This is the exact definition of a restricted eigenvalue. So a matrix M satisfies the restricted eigenvalue with some parameter eta for each vector in this set CS, the norm of m theta square is not too small. And this is the exact quantity of what small means. Okay, so this condition has been well studied in the past decade. We know a lot of families of matrices that satisfies this restricted eigenvalue. I mean, a standard IID random matrix, a subgaussian random matrix, taking rows from orthonormal matrices. Many such matrices would satisfy the restricted eigenvalue condition. But what happens is that, like many of these constructions assume IID in this, the fact that the entries are IID. So, but in applications, we would have matrices which have correlations in them. So the entries in the matrices might be correlated. So what happens then? Okay, so that's kind of the setting that motivated this work. So, the motivation is to look at a matrix with correlated entries that is randomly generated by some mechanism. Okay, and there is some prior work in this line of work. So it's known that correlated Gaussian matrices satisfies this restricted eigenvalue condition. That result that be extended to subgaussian rows, and there are some few extensions of this result also. Okay, so The contribution of this work is that to introduce a broad class of correlated random matrices that have an explicit restricted eigenvalue bound. So this is the construction. We're going to start with a fixed matrix X. So this is a fixed deterministic matrix. And we're going to hit it with random matrices. So we take a random subgaussian matrix, phi, and we compute X phi transpose phi. Okay, so that's the matrix that we're going to look into now. So where X is the fixed matrix and phi is a random matrix. Okay, so the main statement of this work is that to show that the restricted eigenvalue bound on these kind of matrices, X phi transpose phi. So the only condition on X, as I said, X is a fixed matrix. The only condition on X that's needed is that the stable rank of X is not too small. So stable rank is the ratio of the Frobenius norm square by the spectral norm square. And it's like a robust surrogate to rank that's used in linear algebra. So under that condition on X, you can use any X. You will have a RE bound, restricted eigenvalue bound for this kind of matrices. Okay, so some of the features of construction is that we can incorporate any fixed matrix X in this construction. A nice property is that the compression, this matrix X phi transpose phi can be stored in order of MD space, whereas if you want to store a typical design matrix of ND dimension, you need order of ND space. So M is much smaller than N, so we get compression. We get an explicit RE bound for each X. So for each X, you get an RE bound. And we have some applications to sparse linear regression with compressed features that I'm going to explain in the next few slides. Okay, so let me jump into the application. So as I said, the reason people look into restricted eigenvalues is that it has applications in sparse linear regression, and we're going to discuss that in the next few slides. So let me motivate this scenario. So let's say that you have n machines who are trying to send some data to a cloud, and each of them creates an observation covariate response variable, so xi, yi, where xi is a d-dimensional vector and y is a real point. Okay, so now you need to communicate these xi's, yi's to the cloud to run a sparse or linear regression problem on the cloud. Okay, so now since xi is high dimensional, a nice way to go about this is to take a random projections of these xi's. So so pick a random matrix phi and take phi xi's and send phi xi yi to the cloud. Okay, so now with this, you reduce the communication because now the phi xi is a m-dimensional vector rather than a d-dimensional vector, and m could be much smaller than d. So you save in the communication cost, and you also save in memory. So this saves the communication by a factor of d by m. So the question now becomes is that when you have access to only these compressed covariate response pairs, these phi xi yi, can you still estimate theta star? Okay, so the linear model is y equal x theta star plus omega, but you only have access to the compressed version of them, xi's. Okay. So a priori, this is unclear whether this is even possible because you don't have access to xi's, which is needed to run Lasso. You only get a random projection of these xi's. Okay, so one possible option is to look at a slightly similar problem like Lasso. What I'm going to do is I'm going to run Lasso on instead of X Phi, which I don't have access to X. I'm going to run Lasso on this matrix X phi transpose phi and Y, which I have access to. Okay, so this is Lasso on a slightly different matrix, and now we need to understand whether this Lasso on this slightly different matrix succeeds in getting this x theta star, which is a true linear model's parameter. Okay, so it's not hard to show that like parameter error bounds would be ruled out in this situation because we just have a stable rank assumption on X, and we need typically much stronger assumption on X to get a parameter error bound. But what we show is that we can get a prediction error bound. So the prediction errors goes down as a function of the Frobenius norm of the matrix X that you have. So let me conclude. So we have a new construction of correlated random design matrices that have an explicit RE bound and which has application in sparse linear regression. An open problem here is that RE is a special case of a general condition known as restricted strong convexity, and extending these results to this RSC condition would mean that the results extend to other kind of generalized linear models. Thank you.
Thanks. Let's thank the speaker. Quick question? No quick questions? Okay, thank you again.